Now, golden section method, today I am discussing that method, and that method is applicable for finding out optimal solution for one dimensional nonlinear programming problem. Now, golden section method is a method like other elimination techniques like Fibonacci method, dichotomous search and other searching techniques, where we are eliminating the given region, given interval of uncertainty iteratively. But here the golden section method, there are certain things to be mentioned that is very special for this method, is that this method is totally dependent on one ratio, that is called the golden ratio, and there is a history of this golden ratio. I will come to that. Before to that, just I want to tell you that golden section method, it has certain advantages, certain disadvantages as well. The basic assumption for applying this method is that function must be unimodal within the given interval of uncertainty. If the function is not unimodal, if the function is multimodal, that means several maxima minima, local maxima minimas are there within the interval of uncertainty, then we have to break the interval into smaller interval, so that in the one part of the interval function is unimodal. Then we will apply the golden section method for obtaining the optimal solution, whether local maxima or minima, and at the end we can approach for the global optimal solution. This is one part. The next part is that golden section method is similar to the Fibonacci method, but one limitation, one restriction is that, not limitation, one relaxation rather, is that number of experiments are not predefined. We are in the process itself we can just select the number of experiments, and we will just prepare in such a way that we will do the large number of experiments to get better approximation, and number of experiment we can just stop according to our tolerance limit. I will just show you in the next how to adopt that fact in the process. That is why with that let us start the golden section method. Since this is the iterative process again, our task is to learn the whole process of iteration, and I will just show you how stepwise the process is running from the initial interval of uncertainty to the final interval of uncertainty. But everything depends on one thing, is that is called the golden ratio, and this is by convention we are writing the golden ratio with gamma. And this ratio, first let me tell you the value of this ratio. We will see this value is almost same as 1.618. I will first say how this value is coming. After that we will use this ratio in our iteration process. The golden ratio again little more it's a little dependent on the Fibonacci method, Fibonacci numbers, not method, Fibonacci numbers. As we know, in the Fibonacci numbers, Fn is equal to Fn minus 1 plus Fn minus 2. That is, any Fibonacci number is the sum of the previous two Fibonacci numbers in the sequence. Then from here, if we just divide both sides with Fn minus 1, then we are getting Fn divided by Fn minus 1 is equal to 1 plus Fn minus 2 divided by Fn minus 1. And after that, as I said, that we are ready to do large number of experiments, and we will get ratio from this equation only by taking limit n tending to infinity, and by considering gamma is equal to limit n tending to infinity Fn by Fn minus 1. If this is gamma value, then we will see that this will be same as Fn minus 1 divided by Fn minus 2. This will be same as limit n tends to infinity Fn minus j divided by Fn minus j minus 1. Alright. If this is so, then this equation can be written as gamma, this is by considering n tending to infinity, Fn by Fn minus 1 is equal to gamma is equal to 1 plus, and this is 1 by gamma, because this value is gamma only, then this is 1 by gamma, and from here we are getting one second degree equation, gamma square minus gamma minus 1 equal to 0. And since this is a polynomial of degree 2, we will apply the process to get the root of these equations by considering minus b plus minus root over b square minus 4ac divided by 2a. If we just consider, we will get two roots of gamma, 1 plus minus root 5 divided by 2, plus minus root 5 divided by 2. And if we just consider the positive value of this gamma, the positive value, that means 1 plus root 5 by 2, this value will be almost is similar to 1.618. And just look at the thing that if we consider gamma is equal to limit n tending to infinity fn by fn minus 1, we are getting the value of gamma as 1.618, and this is the golden ratio value. And since we are getting another root here, that is the negative root, and that negative root would be is equal to minus 0.618, and if we just consider the root, and we will say that the other root 0.618, this is the conjugate root rather conjugate golden ratio. And what is the value for this? This is equal to 1 by gamma only. That is why we are getting gamma is equal to this, and 1 by gamma is equal to 0.618. These two facts we will use in the next, in our process, in our iteration process. Now, gamma has some historical background, this golden ratio. If we just look back the history of the golden ratio, we will see that if we consider actually ancient Greek architects, they believed that if we consider a room where the size of the room is like this, the larger side of the room is A and the smaller size of the room is B, and it was a belief by the Greek architect that the room is having the pleasing property if the ratio of the whole divided by larger, ratio of the whole to larger is equal to a ratio of the larger to smaller. If we consider, that ratio will be always equal to gamma. That is why if they were believing that if we consider the room, the construction in such a way that the larger side plus the smaller side divided by larger side is equal to gamma, or the larger side divided by smaller size is gamma, then room will be a nice room. But this is one of the fact. And another fact, if we go back to the history of the golden ratio, it has been mentioned in the Euclid geometry that if we just divide a line segment into two unequal parts, then we will see that the length of the whole, that means we are considering the whole line, the larger part is A and the smaller part is B, then the length of the whole divided by the larger part is equal to length of the larger divided by smaller. That is the ratio, again it would be is equal to gamma. And this golden ratio has some significance, and other cases also we will see in the natural objects. People are using golden ratio for selection of the size of the postcard, size of the widescreen TV, and they are considering the sides of the object in such a way that the total, the ratio of the whole, that is the smaller plus larger to the larger is equal to larger by smaller, then it will have a pleasant nice look of that object. This is the beauty of the golden ratio. Now, let us not go into detail about that. We will use this ratio in our iteration process in the optimization technique in the next. The only fact we are considering the golden ratio is gamma, and we are considering gamma is coming from the Fibonacci number by considering the number of experiments infinite, and the value is 1.618. Let us start our iteration process. And objective of the process is to get the minimum or maximum of a nonlinear function that is single dimensional considering one variable. Function can be discontinuous as well. For that case also it is applicable. The step 1, it is only given the initial interval of uncertainty. Number of experiments is not needed for us, that is why we will start with our process from initial level of uncertainty L naught, that is from, let us consider it from A to B. Step 2, we will consider two experiments x1 and x2 within A to B in such a way that it is L2 star distance apart from both the ends. What is the value of L2 star? Value of L2 star is equal to 1 by gamma square L naught. How we are getting this value? If I just go back to the Fibonacci method, we saw that the L2 star is equal to Fn minus 2 divided by Fn L0. Now, here since this is the golden section method, we are considering limit n tending to infinity, large number of experiments we want to do. That is why let us do certain simplification here. We are considering Fn minus 2 divided by Fn minus 1 into Fn minus 1 by Fn and L0. As we know, limit n tending to infinity Fn by Fn minus 1 is 1 by gamma. That is why this is 1 by gamma, this is 1 by gamma. That is why altogether it is coming as 1 by gamma square L naught. Alright. Once we are getting so, then our task is easy to generate x1 and x2. x1 is equal to A plus L2 star and x2 is equal to B minus L2 star. And we will find out the functional values fx1 and fx2, and if we see that fx1 is lesser than fx2, for minimization problem we will conclude that, say the function is this one, this is my function. What we see here, at x1 whatever functional value we are getting, x2 the functional value is higher. That is why we are having this relation here. And if this is the minimization problem, for the minimization problem what we will do? We will discard the interval x2 to b. And what about for the maximization problem? Since the function is unimodal, the maximum value cannot lie here because it is having only one maxima in this function. That is why function could be like this, in this way. Then in that case we will discard other part, that is from A to x1. Once we are reducing the interval, my next interval of uncertainty would be either from A to x2 or from x1 to b. Alright, that is why I will move to the next step, step 3. Step 3, we will have the new interval of uncertainty, it would be either from A to x2 or from x1 to b. Now, what is my next task? My next objective is to find out a2 x2 in between x1 is there. Again we will find out another approximation, we will do another experiment which will lie within the point a2 x2 in the first case. Say x3 is here. How to generate x3? For that thing we have to find out L3 star. L3 star would be is equal to 1 by gamma cube L naught. How we got it? Again with a similar process that can be written as limit n tending to infinity, just like the Fibonacci method, fn minus 3 divided by fn L0. That can be written as limit n tending to infinity fn minus 3 divided by fn minus 2, fn minus 2 divided by fn minus 1, fn minus 1 divided by fn L0. As we know limit n tending to infinity fn by fn minus 1 gamma, then it must be 1 by gamma, this is 1 by gamma, this is 1 by gamma. That is why we are going to gamma 1 by gamma cube L naught. Now, just see the process, we have considering 1 by gamma cube. What is the value of gamma? Here we are considering the value of gamma as 1.618, rather 1 by gamma is 0.618 as we got it from the golden ratio. Then what is the next interval of uncertainty? We will move to the step 4. We will get the next interval of uncertainty, that is L3. What is the value of L3? Value of L3 would be again that would be is equal to L2 minus L3 star, rather this would be is equal to fn minus 2 divided by fn L0, limit n tending to infinity, if we consider this way, and that would be is equal to 1 by gamma square L0. In the previous case L2 was is equal to 1 by gamma L0. L3 is getting 1 by gamma square L0. That is why in general we can say that to generate the jth experiment, we are doing large number of experiments. If we do large number of experiments, that means we are approaching to the optimal solution in a better way, rather we are getting interval of uncertainty with smaller and smaller width, and that is more desirable to us. That is why to generate the jth experiment we can generate the formula for the iteration as Lj star is equal to, very nice to remember, 1 by gamma to the power j L naught, and the jth interval of uncertainty would be is equal to 1 by gamma to the power j minus 1 L naught. We need not to use any Fibonacci number anything, just to understand how we are reaching to this formula we have just employed the definition of gamma here. Otherwise without using the definition very easily we can generate this formula for golden section method, and by just supplying the value for j is equal to 1, 2, 3, 4 we can move to the in the respective steps of the process, and where to end, that is the more important thing for us. That is why we will conclude in this way. We will just see the length of the interval of final interval of uncertainty up to the jth experiment. If we see that length of Lj is lesser than a very small positive value epsilon, then we will conclude that stop the iteration process and declare that Lj as the final interval of uncertainty. And certainly the middle point of the final interval of uncertainty would be the optimal solution of the problem. That is the whole process. As you have seen, the process is very easy to handle, computation process is very easy, only thing is that we have to use the golden ratio value and we have to remember this formula. Let us apply this technique for certain problem in the next, and let us see how the iteration can proceed further. Let us consider the example. Minimize f(x) is equal to 4x cube plus x square minus 7x plus 14 within the interval 0 1 using golden section method. Now, if we just see the property of the function, function is given to us, initial interval of uncertainty is given, it is assumed that function is unimodal in the given interval, otherwise if we just draw the graph of this function, we will see function is very much unimodal. It is having only one minimum value within 0 to 1. That is why let us start our process. What is the first step? First step is that L naught is given to us, that is the initial interval of uncertainty. The length of L naught is 1, and another thing we may consider, otherwise we can may not consider also, as a stopping criteria of the iteration process, we are considering a stopping tolerance epsilon is equal to 0.15. We may consider, we may not consider. Once we are considering the stopping tolerance, that means in the process we will just check what is the length of the Lj, and if it is lesser than this, then we will conclude the process. We may not consider also, in the process we can just generate our stopping criteria. Let us move to the step 2. What is step 2? We are having 2 points. What we see at the functional value at 0 and 1, at 0 the functional value is coming 14, and at 1 the functional value is 12. We need to generate 2 experiments in between 0 to 1. One is x1, another one is x2. How to get x1 and x2? It must be L2 star distance apart from both the ends, that is by the consideration of the golden section method. What is L2 star? We have just considered L2 star is equal to 1 by gamma square L naught. We know 1 by gamma is equal to 0.618. That is why it must be is equal to 0.618 into 0.618 into L0, that is equal to 1, and we will get the value as 0.3819. That is why once we are getting this L2 star, x1 would be is equal to 0.3819 and x2 would be is equal to 1 minus L2 star. It is equal to 0.6181. This is equal to 0.3819 and x2 is 0.6181. Let us see the functional value at x1 and x2. Functional value at x1, it is equal to 11.6953, and if we just substitute the value x2 in the given function, we will see the functional value which will come as 10.9999. And if we draw it here, what we see at x1 it is having higher value 11.6953 and x2 its lower value 10.99. Since the function is unimodal, we want to get the optimal minimum value, that is why we will discard this interval, because fx1 is higher than fx2. We will discard this interval and my next interval of uncertainty would be x1 to 1, alright. in between x2 will be there. X1 is equal to 0.3819, x2 is 0.6181 and this is my the last B value. Now, my next step, we are moving to the next step. We have to generate the next approximation for the optimal solution, that x3. How to generate x3? For that thing we need to generate L3 star, and we will get L3 star is equal to again the same gamma cube L naught, and x3 will be such that it would be the current two experiments, that is x2 and x3, both will be L3 star distance apart from both the ends. That is why this would be L3 star, this length, again this length will be L3 star. Alright, that is why we will get L3 star is equal to 0.2361. Certainly we will get x3 is equal to 1 minus L3 star, and this is coming as 0.7639. And let us see the functional values again. And one thing I must mention here, that if we just see the interval of uncertainty after second step, the whole length is L2, this length, and this L2 would be is equal to, according to my formula, 1 by gamma L naught. Here we are moving to the next step, we will move to L3, we will see L3 would be is equal to 1 by gamma square L naught. We want to achieve this value, let us see. At point x1 the functional value is 11.6953, at point x2 it is 10.99, and if we just go for fx3, this value is coming as 11.0193. This is the value for this 11.0193. Then since the function we want to achieve the minimum of this function, that is why certainly we will discard this region in the next iteration. That is why my L3 will be from this point to this point, that is from x1 to x2. In the next step, let us move to the next step, and if you just see the length of L3, it will come as 1 by gamma square L naught. Step 5, step 4. My interval of uncertainty is from x1 to x3. The value of x1 is 0.3819, x3 is equal to 0.7639, in between we are having x2, this is 0.6181. We have to generate the next experiment x4. For that to generate x4, we need to define L4 star. L4 star would be is equal to 1 by gamma to the power 4 L naught, that would be 1.1459. Then x4 will be is equal to, and again the value of x4 will be such that current two experiments, that is x4 and x2, that would be L4 star distance apart from both the ends. If we just see the distance between x2 and x3, we will see that this is L4 star. Then certainly x4 must be here. Here it would be L4 star distance apart. That is why x4 would be is equal to x1 plus L4 star. That is, if we just add together, we are getting x4 is equal to 0.5278, and with the functional value x4 is equal to 11.1721. Then let us draw the values in the graph. We are having 11.69 something, at x4 it is 11.172, at x2 it is 10.9999 and it is 11.01. We are considering the assumption that the function is unimodal, function is having one minimum within the interval. That is why certainly we will discard this interval in the next step, and we will move to the next interval of uncertainty L4, only this part, and we will see the fact that length of L4 would be is equal to 1 by gamma cube L0, that we can check very easily. L4 is from x4 to x2, x3, we can just see the length. Now we will generate, since L4, the length of L4 is equal to 0.2360, which is equal to gamma cube L0 rather 0.618 to the power q. This value is not less than epsilon, that is why we have to move to the next iteration again, because this length is not small enough to consider as a final interval of uncertainty. We are moving to the next step, step 5. In the step 5 we will generate x5. To generate x5 we will calculate L5 star, and we will see L5 star would be is equal to 1 by gamma to the power 5 L0, and this value is 0.0902. Once we are considering so, we will see x5 will be is equal to 0.7639, that is again the same logic. We will consider x5 in such a way that the current two experiments, if we just see the L4 interval, the one end is x4, another end is x3. One approximation is there, that is x2, and another current approximation we want to make, that x5. Then these two experiments must be L5 star distance apart from both the ends. That is why x5, if we just see the distance between these two, x2 and x3, we will see that it will be is equal to 0.0902, and x5 will be is equal to, that is why this will be minus, certainly one thing is that this is x5 will be here, alright. And this distance is, we will see if I just draw the graph once more here with the point x4, x2, x3, then we will see this is L5 star, this distance, and we will consider x5 in such a way that it is in between, alright, and this value will come as 0.6737, and with the functional value x5 is equal to 10.9611, alright. And if I just draw the function once more here, and another thing, if I just see the length of this interval L5, we will see that it would be is equal to 1 by gamma to the power 4 L0, and that is coming, the value is 0.1458. That is why this is lesser than epsilon. We have considered epsilon, we considered as 0.15, that is why we can conclude this is lesser than epsilon, that is we are stopping our iteration process. But let us see which part of the interval we will discard in this range. We are having x4 as 11.172, x2 as 10.99, x5 as 10.96, lesser than that, and x3 as 11.01. What we see? We see that this is the less x5, fx5 is less than fx2, that is why we will discard this interval, since the problem is the minimization problem, and we will declare the final interval of uncertainty L5 is equal to from x2 to x3, and this length will be is equal to 0.1458, and this is the whole process of golden section method. Now, whatever we have done till date, these are the elimination techniques we have considered, starting from the exhaustive search, dichotomous search, interval halving, Fibonacci method, golden section method. Now, since we have learned all the methods one by one, we need to do the next analysis. Which method is the best method among these? Which elimination techniques gives us the better result? Rather, with lesser number of iteration, we will get the result. With lesser number of calculation, lesser number of experiments, we are getting the optimal solution. That study we have to do. For that thing, we have to measure the efficiency of the different methods. That is why we are moving to the next. That is all about golden section method. We are moving to the next, that the efficiency of the region elimination technique. If L0 is the initial interval of uncertainty, and if we just do n number of iterations, rather n number of experiments, if we just generate one by one, as I have shown you, that then Ln will be the final interval of uncertainty, and measure of efficiency will be calculated as length of the interval of uncertainty after nth experiment divided by length of the initial interval of uncertainty. Rather, this will be is equal to Ln by L0. This is also named as the reduction ratio, and we call it as R dot R. Let us see what are the different values for different searching techniques one by one. If I just see this table, we have considered here different elimination techniques, starting from exhaustive search, dichotomous search, interval halving, Fibonacci method, golden section method, and we are having initial interval of uncertainty L naught. We will see the final interval of uncertainty, then we will go to the reduction ratio. One by one we will just move. In the exhaustive search method, we have seen that Ln was coming is equal to 2 into L0 by n plus 1. That is why the reduction ratio is coming as Ln by L0. Since this is so, then this is equal to 2 by n plus 1. What is n? N is the number of experiments. If we do 2 number of experiments, that is very less for iteration, that should be 2 by 3. If we do 6 number of experiments, that would be 2 by 7, that is the reduction ratio. For the method which is having lesser reduction ratio, that method is much efficient for us. Let us go for the dichotomous search. If we just see the dichotomous search technique, we will see that Ln can be calculated as, in the dichotomous search technique there is another not only L naught, there is another parameter is also involved, that is delta. Generally we are considering the value of delta as very small, but still if we just find out the final interval of uncertainty, this would be is equal to Ln by 2 to the power n by 2 plus delta into 1 minus 2 to the power 1 by 2 to the power n by 2. This is the final interval of uncertainty. If we just see the reduction ratio Ln by L0, delta is very small, that is why we can ignore this part. That is why we can say it is almost same as 1 by 2 to the power n by 2. That is for the dichotomous. What about interval halving? Interval halving technique Ln is equal to, we have learned this is half to the power n minus 1 by 2 L0. And if I just see the reduction ratio, this is equal to 1 by 2 to the power 1 n minus 1 by 2. Fibonacci method, we have learned Ln is equal to 1 by Fn L0. Rather this is 1 is nothing but F1 L0. That is why ln by L0 would be is equal to 1 by Fn. What about golden section method? Just now we have seen that the golden section method ln can be calculated as 1 by gamma to the power n minus 1 L0. That is why we can say this is equal to 1 by gamma to the power n minus 1, rather this is equal to 0.618 to the power n minus 1. This is we could see this is one at a glance we could see the different reduction ratios of the different searching technique. Let us move to the specific value of these reduction ratios for different cases. For 2 cases let us consider the thing. One is that we are considering the reduction ratio when we want to achieve 10% of exact value, that is we are fixing the tolerance of error would be 10% on either side. We are saying either side because as I have said that the final interval of uncertainty is the interval where we say the optimal may lie. But if I want to have the optimal value within that interval, always that would be the middle value of that range. That is why if ln is the interval of uncertainty, this is the ln for us, then optimal must be at the middle point, x star is the middle point. That is why if I want to have the 10% of the 10% of the exact value, rather 10% of the initial interval of uncertainty, if I want to have it in other way, then ln by 2 must be less than is equal to L naught into error we are allowing, alright. This is the calculation we are just doing. We are considering again all the techniques one by one. We are considering the elimination technique by considering L naught equal to 0 to 1 for specific values we are just walking, and 10% of the exact value we are considering as a error. That is why ln by 2 must be less than is equal to L naught by 10. And if we consider 5% of exact value as the error limit, then it would be ln by 2 must be less than is equal to L naught into 5 by 100. That is why we are getting ln less than is equal to L naught by 10. If we just calculate for all the searching techniques one by one. For exhaustive search, as we know the reduction ratio ln by L0 is equal to 2 by n plus 1. That is why 2 by n plus 1 must be less than is equal to 1 by 5, because if I just go 2 will come here and it will be 1 by 5. And from here we can calculate the value of n greater than equal to 9. That means we need to do at least 9 number of experiments to get this level of accuracy. And for the other thing, if we consider 5% of exact value, we have to have at least 19 number of experiments, rather 19 number of approximation, 19 approximations we have to make to get the accuracy of 5% of exact value. This is for exhaustive search. This is for dichotomous search, as this is the reduction ratio. 1 by 2 to the power n by 2 must be less than equal to 5. We can calculate n must be greater than equal to 4. If I want at 5% of exact value, then we have to do at least 6 number of experiments. Similarly for others, if I just see for the interval halving technique, we are having n must be greater than equal to 5, but for 5% accuracy we must do at least 7 number of experiments. For the Fibonacci method, this is the reduction ratio 1 by Fn, just now I have showed you. Then from here we can deduce that n must be greater than equal to 5. But if I want to have the 5% accuracy, n must be greater than equal to 7. And the golden section method, we are getting n must be greater than equal to 5 for 10% of exact value if this is the error tolerance, and if I want 5% of exact value, then n must be greater than equal to 6. This is some calculation I made, but if I want to do more calculation, we will see that Fibonacci method is the best method, among all these searching techniques. Why it is best? Because the computational process is very easy, this is one part, but the most important part is that we need to do less number of experiments for even for better accuracy. If I want to have 1% of exact value, error limit, if we just tolerate 1% in either side of the exact value, then we need to do less number of experiments than any other method. But one thing must be mentioned here also, that golden section method, this is also very much similar to the Fibonacci method. That is why golden section method is also a very good method for efficient method, effective method for finding out the optimal solution for nonlinear optimization problem, single dimensional optimization problem. And one thing, it is known that Fibonacci method and the golden section method is almost identical to Fibonacci, because this is very much asymptotic to the Fibonacci method. Because as we know that if I just increase the number of experiments n tending to infinity, then Fibonacci method is same as the golden section method. That is why these are all the region elimination techniques I just wanted to discuss all just at a glance. This is the comparison of all methods. Now, let us move to the next, that is the problems which you can address for practice. These are the examples. We can consider. We can consider the function f(x) as sin x to the power 6 plus tan into 1 tan 1 minus x e to the power 30x, where function is in between 0 to 1. We need to find out the maximum of this function by Fibonacci method and golden section method both. You can do it. And we can consider another function, minimization of f(x), which is equal to e to the power minus x plus e to the power x, and the function is defined within the interval minus 1 to 1. Function must be unimodal within this interval, then only the Fibonacci and golden section method both are applicable. That is why that can be tried. We can see the optimal solution for this function, that is the minimum of this function, using Fibonacci method and golden section method separately. Let us consider another function, that is function f(x) at 1 minus x into e to the power minus x square. We have to minimize f function, and both the function can be minimized using Fibonacci method and golden section method. That is all about the region elimination technique. Okay, let us take another example as well. This example I have considered from the book written by Professor S.S. Rao, Engineering Optimization Theory and Practice, and this is a problem for us. Find the value of x in the interval (0, 1), which minimizes the function f(x) is equal to x into x minus 1.5, and one error limit is given also here to within plus minus 0.05. That much error is allowed by golden section method and by Fibonacci method as well. Let us consider another example in the next, that is the function I am just writing, that can be, all the methods can be applied here. Just see the, you can do the comparison of the processes. Minimize f(x) is equal to x to the power 5 minus 5x cube minus 20x plus 5 within the interval 0 to 5, and the methods have you can adopt unrestricted search method by considering step size .1 and starting point 0 x equal to 0. Then we can apply the exhaustive search within the whole range. We can apply the dichotomous search. And as we know, there is a parameter for dichotomous search. We can consider a very small value for delta, that 0.0001. We can apply the interval halving technique. Apply Fibonacci method. Apply the golden section method. And Fibonacci method, here you can consider %% of initial interval of uncertainty. That is 5, that is error limit, and golden section method according with a smaller interval size, and that is all about the elimination technique we can implement for solving nonlinear one dimensional nonlinear programming problem. Thank you for today.